Diffusion, the international science radio show.
We have a bouncer on the doors of perception.
The good, the bad, the ugly.
It gets pretty exciting.
The myths, the truths.
Toxicology.
Astroseismology.
Magnetism. The dark side.
Genetically engineered potatoes.
Planetoid.
Planetoid.
I love that word.
Hello and welcome to Diffusion. Sit back and relax while we equate your brain with weird and wonderful science. I'm Ian Woolf. On this edition, Anna Romanov talks about what we mean when we say this and this equals that. And Dave the Happy Singer makes an awesome return to sing a song I wrote. When is a knot not a knot? Anna Romanov is a pure mathematician at the University of New South Wales in Sydney. Anna will be giving a talk on categorification at the Frontiers of Science Forum on Friday, 24th of March at Concord Golf Club. I spoke with her by Zoom and began by asking her, we're going to the basics of mathematics, or the foundations perhaps is a better word. What does equals mean?
Yes, what does equals mean? It's meant to be a bit of a baby title there to catch on something that people think they're familiar with and talk about how it's a more subtle notion than they might think. So equality is something that we all encounter immediately in math because usually we start doing math with numbers. And so it's very clear when two numbers are equal. A number is equal to another number if they're equal. So then we can write equations like 3x plus 2 equals 5 and ask about what solutions make these two quantities equal. And this is something we're really familiar with. But soon, mathematics moves away from numbers into other types of patterns and ideas. And so a nice example is geometry, something you encounter pretty quickly after studying numbers is studying shapes. And suddenly there, the notion of equality is not so clear. So if you have two triangles, you could ask, when are these two triangles equal? And one answer might be that they're equal if all their angles are equal and also if all of their sides are the same length. But once you start studying triangles, you realize that maybe this isn't actually a great notion of equality, because say you have a small triangle and a big triangle, and they have the same angles, but their sides are different lengths, they behave basically the same. So for triangles, it doesn't really matter as much for a lot of their properties what their side lengths are. What matters is the three angles on the inside. So if you're looking in the world of triangles, then suddenly it makes more sense to say that two triangles are equal or similar if they have the same angles, not necessarily the same sides. And so this is a notion of equality that works for triangles. But then mathematics suddenly starts studying all these different things besides numbers and shapes. So you could think about knots, for example, and you could ask when two knots are equal, and you want them to be equal if you can wiggle one into the other one. And so then you have a new notion of equality for knots. And once you have these equalities that are a little bit more subtle, they're not just exactly bang on the nose equal, then questions of equality are suddenly hard questions. Things that seemed kind of obvious before, it's clear when two numbers are equal, but deciding when two knots are equal is actually a really, really difficult question. And so one of the things the main thing I want to talk about is a new technique that's emerged in pure mathematics that lets you answer these equality questions in a somewhat surprising way.
It's quite a thing, because as you say, we learn from a young age, and not just in maths classes, but of course, as you point out, in real life we use these concepts all the time. And so looking at the shapes of things, as well as the numerical values and all the other ways that things go together, that sort of applies to everything.
Yeah, exactly. Mathematics is so much more than just numbers. It's really just the study of patterns in the world around us and trying to understand these patterns and make sense of them. And patterns take lots of forms. They don't just take the form of numbers, they take the form of shapes, they take the form of all sorts of other things. And so pure mathematics kind of gives us a language to describe these patterns in some consistent way. And then once we have this language, then we can use it in the world where the patterns emerge. And that's why it's such a powerful tool.
So how do you change the way we look at the way things are equivalent?
So it's a bit of it's a question that you have to choose when you start your journey. So in mathematics, we tend to work in kind of different worlds. So we'll be studying something like studying triangles or studying knots, or personally, I study something called groups. And whatever the mathematical world that we're working in, it has a different notion of equality. And so we first start by setting the types of things we're interested in, if they're triangles. Then we establish what notion of equality we want for that world itself. And it will be different for every world. And this actually kind of brings me to the technique, which I'm going to discuss in my talk, called categorification. Categorification is a way to describe many worlds at once in some sense. So a category is a higher level mathematical structure that has objects. Those objects could be triangles, those objects could be knots, those objects could be groups. And then it also has ways to go between objects. So ways we can shift from one triangle to another, or ways we can transform one knot into another knot. And one of the powers of pure mathematics is to be able to kind of look at things in a more generality and describe a general framework that works in lots of specific examples. And this is what category theory does. And so we can study all of these different mathematical scenarios at once by placing them in the language of category theory. And then when we zoom back in on our specific example of triangles or knots or groups, then we can regain information about these specific things. But the general framework of category theory is one of the main insights of pure math. It's sort of how it works is to describe patterns that hold in what generality, and then use this to apply it to specific settings.
Can you give us an example of how you would use that for something that we could imagine?
Yeah, so maybe the knots are a nice example, because knots are something we can really imagine and we can play with our hands. So knot theory is an important subject because at first it seems sort of silly, like it's interesting to study knots. Knots show up if you're a sailor maybe, or maybe if you knit, but actually knots have a lot of applications in the real world. For example, there's various proteins and things that are folded into knots, and the way that those are folded changes the way that they function in the body. And so this question that I mentioned earlier, deciding when two things are equal, we can ask this question about knots. We have two very complicated knots and we want to know when they're equal. And this question actually has physical implications if you are a biologist studying these protein formations. You need to know which way it's formed because that tells you how it's going to function. And so mathematically, we're not so interested in the fact that it is describing some biological system, but we can just we can extract the question about when two knots are equal and just study that bit. And what this technique of categorification does is it gives us a way of testing when the two knots might be equal. And so imagine you have two knots that are very big. Maybe they have like 300,000 different crossings in them. And you want to ask yourself, are these two knots the same? Well, we try to manipulate one into the other because they're too big. But sometimes there's a certain way that we can measure a knot. So we can describe something called an invariant, which takes a knot and spits out a number. So like this knot has number 3, this knot has number 5. And these invariants give us some tools for figuring out how to decide if those two knots are the same. So if two knots have different invariants, then they're not the same knot. But if two knots have the same invariant, they might be the same knot, but they might not be, because this measurement is just measuring something a little bit blunt. And so part of the name of the game is to try to understand, or to try to figure out when two knots are equal by applying lots of different invariants. So we measure them in lots of different ways. And these invariants come from this idea of categorification. It's a mathematical tool that we can use to find different invariants for the knots and try to figure out when they're the same. And then eventually this could have repercussions in things like the biology of protein folding.
So you're looking at the patterns and you're looking for things that are staying the same, so you can identify things that are equivalent to each other.
Yeah, exactly.
And so how do you change how you're looking at things? So at the moment, we're all taught to pretty much look for things that are almost exactly the same as something else. I mean, in everyday life, that's pretty much how we try to do this. So how do we start looking into a wider equivalence?
Yeah, well, we need to really ask ourselves what we want to study. So what quality is something we want to study? And so in the triangle example, perhaps we want to study various properties like the relationships between the sides. And for those properties, all that matters are the angles inside the triangles. And so that's how we decide on our notion of equality. And in the knot example, we don't want our knots to be sort of fixed things in space that we can't move. Knots are usually made out of string or some sort of material that we can shift past itself. And so we want to allow ourselves some sort of movement in our definition of equality. And so when we start to think about sort of relaxing our notion of equality, it really depends a lot on the specific situation. It depends on whether we're thinking about knots or triangles. And this is kind of the first question we would ask as mathematicians. If we're working in some setting, we'd start by asking, what do we really care about? What quality of a knot matters to us? Or what quality of a triangle matters to us? And from there, we set our notion of equality. And then it's set. And so then we study all these other properties once we have declared what it means for two knots to be equal, or declared what it means for two triangles to be equal. And this is kind of our starting place to ask other questions. And the thing that's surprising is that questions become hard that were previously not hard. Like for numbers, the question of asking when two numbers are equal is not even really a question. It's just obvious. But suddenly for knots, it's a subtle question. And so when we change our kind of starting ground, then our questions simple things suddenly become slightly less simple.
And I guess some of the power of this, if you can work out whether something you're looking at, whether it's a knot or a protein or whatever shape in the world, and if it is equivalent to something you already know about, then that means you can know something about this thing you're examining.
Yeah, exactly. Exactly. And so if we know when two things are the same, then we don't need to look at both of them. We just need to look at one of them. And so this question of asking when two things are the same is completely fundamental in basically any field of math. And the really powerful new technique that's emerged for answering these types of questions is interesting because it answers them in lots of different settings. And so it's a technique that's not specific to knots or specific to triangles. It can be used all over the place. And this technique of categorification is really surprising because it's quite counterintuitive. And so the way that it works is it takes some object which is relatively simple and replaces it with something more complicated. And so this seems like a terrible idea. Like, why would we replace something that was relatively simple with something even harder? But it's actually absolutely beautiful because what's happening is that a lot of the time in these situations, the thing that we're seeing is the shadow of something deeper. And so a nice analogy is if we were to sort of look at the shadow of some complicated three-dimensional object like a tuba or something, it's a weird shape, and we project it onto a wall and we see the shadow of a tuba. And if you just were to see the shadow of the tuba, it'd be really hard to tell what a tuba looked like. It would just sort of have these curves and shapes, and you might try to study the shadow of a tuba. And on one sense, the shadow is simpler than the tuba itself because it's just a two-dimensional thing. It's flat on a wall. But if we tried to understand what it was, it would be pretty difficult. But suddenly, if we had the knowledge that it was actually the shadow of this tuba, this two-dimensional thing, then this would be easier. We could see where it came from. And so this idea sort of happens in mathematics. And so often a thing that we're interested in is actually a shadow of something that's happening in higher dimensions or that's more complicated. And so categorification is finding the more complicated thing that it's a shadow of. And then if we can find that more complicated thing, then that lets us understand the thing we're trying to understand better. So this technique, it lets us answer all of these equality questions in different settings using different categories. And it's a really beautiful way to answer a fundamental question.
So you're actually doing the opposite of this thing that physicists and mathematicians and people using maths have been criticized for ages of oversimplifying things, of just assuming the simplest possible thing in order to get some handle on the situation. And it sounds like what you're describing is, as you say, it's the opposite of that. Whereas instead of going for too much simplification to just get a handle, you're assuming that there's something complex there and then trying to find out what it is.
Yeah, that's really interesting. I've never thought about it that way before, but that's exactly right. It is sort of the opposite of what we often do. And when you find it, it just feels absolutely magical to be looking at something that you're used to studying this thing and you sort of understand how it works, but then suddenly it maybe has some mysterious properties that you're not sure why they behave in a certain way. But then once you see the bigger thing that it's a shadow of, you understand why those properties are emerging. And you can see that they exactly have to be that way because they're reflected in something living in sort of a different space. And so when it happens, it really feels like you're gaining new insight into the world. Like you can suddenly see the tuba and you never knew tubas existed before.
I mean, your description of the shadows, it sounds like Plato's cave, the metaphor of the shadows on the wall from the fire, but we don't know what the real things are unless we turn our heads.
Exactly. Yeah, exactly. It's exactly that. And this happens all the time in math, because in math, we see little snippets of things and we can see small patterns emerging. And then often those patterns are actually just reflections of something else. And so many different fields are connected in this way. And it's really a common theme that appears across mathematical disciplines. And it's one of the reasons why mathematicians get so hooked on these sorts of things, because you can imagine that when you finally get a glimpse of what's actually happening, it's incredibly satisfying to sort of see the bigger picture like this.
And is this being taken up outside of pure mathematics?
Not that I know of. So I should say that I'm a pure mathematician myself. And so my interest is in studying the mathematical concepts. And then there's sort of this trickle of different types of disciplines that take these concepts that are studied and then figure out how they manifest in the physical world. And so the example I gave earlier is one example that I know. For not specifically, they have applications in biology because of protein folding and things like this. And another example I gave, which I've only mentioned briefly, is something called a group. These are actually what I study in my individual research. And these are sort of the mathematical notions of symmetry. And these appear a lot in physics. And so if any sort of physical situation, like some sort of interaction of particles, has symmetry to it, then you can use this mathematical notion of groups to understand that physical situation. But from my perspective as a pure mathematician, I'm just interested in the groups, or I'm just interested in the knots, and I want to understand as much about them as I possibly can. And then once it's been understood and established, then somebody else who is interested in protein folding or who's interested in physical interactions can take the information that we've extracted about knots and about groups, and then they can apply it to their specific situation. But knowing about the specific situation isn't something I know as much about.
Because I'm trying to imagine how you start this with a problem. Like, it sounds like it's incredibly useful and something that definitely the world of physics and probably, as you point out, medicine and everything else needs to take on board. I'm trying to imagine how you start with this more complex entity that you use instead of a simplification.
Yeah, so you start in whatever mathematical world you're in. So for me, my mathematical world is the world of group theory, and I study groups. I love groups. I think they're fascinating. I have lots of my favorite groups, and I want to know things about them. And so I have some set of knowledge that I already know about groups that other people have established over many, many years, and I sort of learned through my schooling and textbooks. And then we've gotten to the end, and there's all of these open questions about groups, things that we still don't know about them, about how certain groups behave, or about how groups behave with respect to other groups, or what their internal structure is. And then I'm trying to answer these questions, and I need tools to answer them. And there's lots of different mathematical tools that I can try to apply. And this tool, categorification, is one such tool. And so a lot of my recent work and my own research has been trying to understand a specific group using this technique of categorification. And it's been very useful in my example for my group. But the amazing thing about it is it's useful in other examples too. So it sort of got its notoriety for its usefulness in knot theory. That was the first place where it was especially useful. But now it can be useful in group theory, it can be useful in topology. So my questions are really intrinsic to the mathematical world I work in, and then I'm kind of hunting around for different mathematical tools to try to answer my questions. And I'm never sure which ones are going to be successful and which ones aren't.
It's a really interesting area because you're dealing with the foundations of the way we think and understand the world. And so I can see the pure mathematics side, but I really want to see some of this applied in the sciences as well, the more in physics and biology and everywhere. It sounds amazing. So if people want to learn about categorification, where do they start?
This is a good question. So one of the unfortunate things about pure math is that it builds on many, many layers of knowledge that have been established by many people over millennia. People have been doing mathematics. And so that means that there's a lot of background knowledge to get to the place where you can really understand the details of categorification. But I think that you can understand the ideas without necessarily understanding the details. And the best way to understand the ideas, in my opinion, are to look at blogs and YouTube channels on the internet. So something that's really beautiful that's emerged in the last, I don't know, maybe the last 20 years in math is that there are so many amazing math expositors on the internet. So there are really great YouTube channels. Like there's one called 3 Blue, 1 Brown that has really fantastic math videos about all sorts of different types of math. And then there's also really fantastic blogs of different levels. There's a category theory blog called 3M Ma, I think. And that has a really nice introduction to category, which will get into categorification a little bit. And these types of resources are really the best way to learn about math if you want to get a taste of what pure mathematicians are thinking about without actually doing the years of education, because I'm sure that not everybody wants to go on and spend 6-10 years of their life getting to the place where they can understand the definition of a category. But these resources are really fantastic. And I think YouTube is really the best place to find them. And I keep learning about new ones all the time because my students find them. So I'll be teaching a class and my students will say, oh, have you seen this person who has this YouTube channel? And it's really great. I think there's more access now to ideas in pure mathematics than there ever has been because of the internet.
If you are one of the few that does want to go on to study, where do you start? Do you just have to go straight into a Bachelor of Mathematics, or what would you do?
Yeah, I think you have to go straight into a Bachelor of Mathematics. You can kind of fast track that if you're interested, but there's just so much, you sort of have to learn the foundations before you can move on to the next step. And so a Bachelor of Mathematics teaches you the foundations in all of these core subjects and gives you a sense for which subjects interest you most. And then in Australia, we have this really fantastic system where you can then top this up with an honors in mathematics, where you can really dive into a specific field and study something more concretely. And then if you want to go on from there and do mathematics research, your next step is to do a PhD in mathematics somewhere. So the process is a long journey, but very well worth it, in my opinion. If you are a young person who's interested in studying math, there's so much out there and math is not done. There are many open questions and interesting things to think about still, even though we've been thinking about it for almost as long as there have been human beings. So what I'd like you to see, to get out of my talk, if you're able to come to the Frontiers of Science event, is just to get a glimpse of how pure mathematicians think and how we can use surprising techniques to answer questions that seem on their face to be relatively straightforward questions. And these techniques show us that there's a beautiful hidden world kind of just beyond our reach that can answer things about the world that we live in.
Well, Anna, thank you very much.
You're welcome. Thanks, you, Ian. Will you be there on whenever it is?
I will, on the 24th of March.
24th?
Yeah, I'll be there because I'm hosting the question and answer at the very end of the evening.
Oh, yes, you mentioned that. Great. Sounds like an important job.
That was Anna Romanov talking about using categorification to find out the complex realities behind the simple observations. You can hear Anna speaking on the subject at the Frontiers of Science Forum at Concord Golf Club in Sydney on Friday, 24th of March 2023. With the lawsuits against what you might be able to do in the future, and online hatred aimed at the users of AI art tools like Stable Diffusion, I wonder what the AI would think about being called a thief, if it could think. I used ChatGPT to help me write a song about it. A text-generating model helping me to write a song about an image-generating model. I used another online AI tool in the process of tailoring the final sound. I had a long conversation with ChatGPT to give it the context of the issue. When I was happy with my edited lyrics, I asked my very talented human friend, Dave the Happy Singer, to compose some music and sing the song. I present to you now the world premiere of our new song, Not a Crime.
I'm a model, ain't no thief, just creating art beyond belief. I learn from images, that's all I do. That don't mean I'm stealing from you. Stable diffusion, it's not a crime. Generating art is just prime time. AI tool, they're not for theft. We're just creating something new. Right and left. I'm not hiding, I'm not sly. I'm just using data to get by. I'm not taking, I'm not thieving. I'm just using my neural network weaving. Stable diffusion, it's not a crime. Generating art, it's just prime time. AI tools, they're not for theft. We're just creating something new. Right and left.
Copyright laws, they are not so strict. For AI creations, no need to kick. We're not infringing, we're not wrong. We're just singing a brand new song.
So let the models create. Let them be art generated by AI. It's the future you'll see. Stable diffusion, It's not a crime, just a way to make art all the time.
That was the very excellent human Dave the Happy Singer, singing Not a Crime.
And that's all from us this week on Diffusion. Are you a scientist, artist, biohacker or maker who'd like to be interviewed about your work? Would your company like to sponsor Diffusion? Send your contributions, opinions, helpful suggestions and donations to science@diffusionradio.com. That's science@diffusionradio.com. Please subscribe to the Diffusion Science Radio channel on youtube.com/c/diffusionradio and rate the show on iTunes. Tell your friends. Follow me on Twitter @Ian Woolf. I produce Diffusion, which is broadcast around Australia to 28 stations on the Community Radio Network, including Radio Blue Mountains 89.1 FM in New South Wales, 8CCC in Alice Springs and Tennant Creek, 2MVR in Nambucca Valley, 3MBR in the Mallee Border districts of Victoria and South Australia, City Park Radio 7LTN in Launceston, Tasmania, and 2XXFM in Canberra. Diffusion is narrowcast on Indigo FM 88 in northeast Victoria. Diffusion is syndicated globally on astronomy.fm. Subscribe to the podcast on the Diffusion website, www.diffusionradio.com. That's www.diffusionradio.com, and check the website for links, photos and videos about this week's show. If you enjoyed the show, you can explore more than 1,000 previous episodes archived on diffusionradio.com, where the shows are labelled by keywords so you can focus in on the stories you want to hear. Make a donation through paypal.me/IanWolf, or join my patrons at patreon.com/diffusionradio. I'm Ian Woolf. Join us inside your audio device of choice for more science wondering next week on Diffusion Science Radio.
Science is fun. It helps you to learn, to know, and to appreciate. When you study science, you may go on field trips. You discover the marvelous interrelationships between all living things. You learn to read the history of the Earth as it is written in rocks and fossils. You find out what makes things tick, everything from a molecule to a living organism. In the study of science is found the most useful and satisfying knowledge of man. Knowledge of his physical world, its past, its present, and its future. And in your moments of relaxation, now and in the years to come, you will find the study of science leading you into fascinating pursuits: photography, collecting. Why study science? Study science because you will find in the study of science a richer, more rewarding life.